Welcome back, class. I thought it would be nice now to include a lesson on series resonance. And once again, I'm going to take a mathematical approach to this topic. Let's just start by reading the top line. It says, at the resonant frequency, which is denoted F with a little subscript of R, the magnitude of the inductive reactance equals the magnitude of the capacitive reactance. Okay, so we already know that in terms of direction, inductive reactance would be on the positive imaginary axis, and capacitive reactance would be on the negative imaginary axis. But we're suggesting that at resonance, the magnitudes of the two quantities are equal. So what does that mean? Well, if XL is equal to XC, then our impedance formula would have these two portions canceling each other out. And you are left with simply this. The impedance is equal to the resistance. So in this case, we say that the circuit is purely resistive. Not only that, if there is no imaginary number associated with the impedance will be at its minimum. So I think I'll just go through a couple of interesting examples with you. So here we have an RLC circuit. We have 200 ohms for the resistance. We have a 250 millihenry inductor and a 20 nanofarad capacitor, and these are connected in series to our AC source. So let's try this problem. Determine the resonant frequency for the circuit below. Okay, so let's give this a try. So I'm going to make note of the values that we have. So we have 200 ohms. We have 250 millihenries. And we have 20 nanofarads. And what are we trying to find? The resonant frequency, which remember we can symbolize this way. So what we can do is start with the fact that at this frequency, we will have XL equal to XC. And what does this mean? This means 2 pi FL will be equal to 1 over 2 pi FC. And notice I've got a little subscript of R on my frequency. So what I'm going to do is try to come up with a formula now for FR. So to do that, the first thing I'm going to do is cross multiply. So I'm going to take 2 pi FL and multiply it by 2 pi FC on the left side, and on the right side we'll just have 1. Okay, so when we multiply this by this, notice that we will have the 2 pi F all squared, and then multiplication by L and by C. All right, from here now, I'm going to try to come up with a formula for that resonant frequency. So first I'm going to isolate this portion right here. So that means dividing both sides of the equation by L and C. So this will look like 1 over LC. All right, so now if I'm trying to get to the FR in here, I have to eliminate the square. And of course, we do that by square rooting. And And instead of trapping this fraction all underneath the square root sign, I'm only going to show the square root sign in the denominator over L times C. And that's because the square root of 1 would remain 1 anyway, like that. Okay, last step to get FR by itself is just to divide both sides of the equation by 2 pi. And so that gives us this final equation. The resonant frequency is equal to 1 over 2 pi times the square root of L times C. All right, so again, we first started by setting XL equal to XC, then I cross multiplied. I just divided both sides by L and C in order to isolate this quantity that has the square, since F is inside that bracket. Then I had to square root both sides, and lastly divide by 2 pi. So here we have it, a formula for resonant frequency. You can see that it doesn't depend at all on the resistance value here. So we will not even need to use that value to calculate this resonant frequency. Okay, so underneath the square root sign, I have 250 milli multiplied by 20 nano. Like that. Okay, so that's just substituting into the formula. And now we're going to go ahead and work this out. So I could do it all in one step. Although I might want to just show you that you could work out 250 milli times 20 nano first. You might like that better. So 250 milli multiplied by 20 nano is this number, 5 nano. So now this is what we need to work out with our calculators. Now, as I showed you in the last lesson, when I have one of these 1 over formulas, I simply like to punch in the whole denominator. So I would do 2 times pi, which I think is fine just to say 2 pi, okay, times the square root, oops, I did cube root, sorry, back. Square root of 5 nano. Okay, just like that, 2 pi times square root 5 nano. Push equals. That's an answer for the denominator here. But what I would like to do is invert that answer now. So we simply hit x to the -1 and then equals. And I'm going to round this answer to 3 significant digits. It is 2.25 kilo ohms. Okay, so just like that. If I didn't first work out this number, I could do this calculation like this. So 2 pi times square root. Now I would need a bracket around 250 milli times 20 nano. Close the bracket, push equals. Okay, so if there's an operation to be performed under a square root sign, you need to bracket it like that. So that's the denominator, and that's the answer. Okay, so I wanted to show you that problem to begin with. Calculating the resonant frequency for that given circuit, and the interesting part being that it doesn't matter what the resistance value is. And now let's go on and do this question. It says, a 5 millihenry inductor and a capacitor are connected in series in the circuit of a receiver for navigation signals. Determine the capacitance if the resonant frequency is 25 kilohertz. Okay, that's a lot of language. So we're gonna start the problem just by writing down the quantities that we are given. All right, I probably have room just to do that question here, but maybe to be safe, I'll go to, I think we're good here. Okay, problem 2. So what quantities, we've got to save those trees. What quantities are we given? We're given 50 millihenries. So we know that that is L. What else are we given in this problem? Resonant frequency, and we know that that is FR. Okay, so it is 25 kilohertz. So again, let me just show you that. We were given 50 millihenries for the inductance, so that's capital L, and the resonant frequency, which is FR, 25 kilohertz. What are we trying to calculate? The capacitance, which is capital C. Okay, so you can do this in a number of ways. I think I'm going to do it using a similar method to what we did here. So I'm going to start by saying, well, if we're at the resonant frequency, then we know XL equals XC. So 2 pi FL is 1 over 2 pi FC. Like that. Okay, so this is the same way we started the previous question. But this time we're going to solve this equation for C. So how do we do that? Well, we'd cross multiply next in this way, and that would give us 2 pi F all squared LC is 1. Okay, so these are the same steps we did here. Look, here, here, here. Only now, if we want a formula for C, all we have to do is divide 1 by everything else. And we're done. That's the equation we can use for capacitance. All right, so all I have to do now is substitute 25 kilohertz here and 50 millihenries here, and I'll be done. I'll have my answer to problem 2. Okay, so within this bracket, we have 2 times pi times 25 kilo. That has an exponent of 2 on it, and the inductance is 50 milli. And I have to just ensure that I put this into my calculator correctly. So once again, it's a 1 over formula. Let's begin by getting an answer for the denominator. So I'm going to do it like this, bracket, and in the bracket we're going to do 2 pi times 25 kilo. We have to close the bracket, and we need to square that. That's the x squared button. Now, implied here is multiplication, so I need to do times 50 milli. Push equals. So that's an answer for the denominator. Now we invert the answer with the x to the -1 button here. And we have the capacitance. And if we round to 3 significant digits, which is what I did in question 1, and I was just following the same instruction for rounding that we had in the last lesson, okay? So if we round this one to 3 significant digits, you can see it's 811, and don't forget pico right here is the prefix. And you have to remember that you have just calculated capacitance, and therefore that is measured in farads. Okay, so that's all there is to it. Note that if you had a question where you were given the capacitance instead here, so given the capacitance and you were given the resonant frequency and you were asked to find the inductance, you would do this, 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 and then how would you get a formula for L? You would simply put L equals 1 over 2 pi f all squared times C. In other words, the L would go here and the C would go here, and that's all there is to it. Okay, so I like these methods of solution for these problems because they're very mathematical. You get to practice your formula manipulation. But I will say that there is another way that you could have solved this problem, and maybe some of you are thinking that what you could have done instead is first taken these two quantities and used the two quantities to compute XL. And then once you had XL, you would know that that is also equal to XC. And then having XC, you could figure out the capacitance. So maybe I should show you that here as well. Maybe you're interested in that. So why don't I say that's solution A. And now I'll show you a second possibility. So for that same question, if we had the same values, so remember we still have 50 millihenries, 25 kilohertz, and we're trying to figure out the capacitance in farads. What you could do is calculate XL first. So this is 2 pi FL. So 2 pi times 25K times 50 milli. So 2 pi times 25K times 50 milli. It's this number, okay? And I'm gonna keep 3 decimal places here. 7.854 kilo ohms. Okay, keeping 3 decimal places, not 3 significant digits, because this is not a final answer. The final answer will be for the capacitance. And then once you have that value, you know that that is also equal to XC, since we are at the resonant frequency. And then the formula for XC looks like this. So what you could do is simply rearrange it. And you would have C is 1 over 2 pi FXC, like that. That's the correct way to rearrange that formula. And now we know we would have 25 kilo here and 7.854 kilo here. And I'll just punch that in. We're hoping it'll match the 811 picofarads that we got solving this the first way. Okay, so 2 pi times 25 kilo times 7.854 kilo. That's an answer for the denominator. invert it, and it would round to 811 picofarads once we rounded to 3 significant digits. Okay, so you have a choice. You could either solve it this way by simply manipulating the formula and only making one actual physical calculation, or this way, which starts with the XL calculation. Okay, so that's all I wanted to review with you in this video. Actually, there's only one more video available for this unit, and what we're going to be doing in that next video is looking at not series circuits but series parallel combinations. So that's quite interesting, and I look forward to sharing that with you. Thank you.